morning, everybody. Welcome back to Galois Theory. How are y'all doing today? I don't actually care. Hope y'all had a good spring break. Plan for today, we're going to talk about do some algebra. We're going to talk about algebraic extensions.
I love that.
And talk about what's the difference between an algebraic number and a transcendental number.
Is that the movie today? In honor of Pi.
No. Say what?
In honor of Pi.
No, just because that's what we were going to do today, regardless of what.
But it is our first class since Pi Day.
Sure. Okay, fine, whatever. Office hours. I've got my usual office hours this afternoon 1 to 2, tomorrow morning at 11, tomorrow afternoon at 1. You have a homework due today. Make sure I get it by the end of today, or by the time I get in tomorrow morning at least. Exam coming soon. It's about time for you all to have a midterm. So, what's midterm for this class going to look like? It's a take-home exam.
Yay!
Partner?
I will let you have a partner.
Yay!
Yay!
So, those of you who haven't had this experience in Dr. Gersel class, what does that mean? It means you are allowed to work with one other student on formulating ideas for the exam and like talking about problems and such. However, you need to write up your submissions for the exam on your own. No copying off of your partner or any nonsense like that. But you're certainly allowed to work together, talk, share ideas, and then go off on your own and write up your work, though. I love this because, I don't know, this is a pretty abstract class, you may have learned. And sometimes it just helps to have people to share ideas with, talk with, other than me. So it'll allow you to work with one partner. And no, none of this nonsense where Andrew works partners with Isaac, who partners with Jonah, who partners with... None of that nonsense.
We can't form a sickly group?
Shut up. What?
Talking only in one direction, the other person is silent the whole time.
No, not allowed.
Allows you to tell it that.
Because I can still get like one person. No. So what's the plan for the take-home? The plan is I get the take-home out on Thursday and it's due next Thursday. So I'll have a week to work on it. Hoping to have it done by like tomorrow afternoon, but if not, it'll be done on Thursday. So you have a week to work on it. It's whatever percent of your grade, I forget. Essentially, think of it as being like a homework that's...
It's only 5% of the grade, right? Yours?
I don't remember, but I assume
It's
it's
about
more
5.
than
Yeah.
I think it's 30.
It's like 3%, right?
Thirty.
Like 2%. I think it's
Probably
like
15. Because I'm pretty sure that's what they've been in
I think
past
it was
classes.
like
No.
Whatever it is,
I think it's actually
whatever it is, I'm pretty confident it's more than 5.
Yes, it was close.
It's actually
20.
Yeah.
20%.
20%. Also, hey Lydia, if you're listening to this, you are allowed to have a partner as well, if anyone wants to work with Lydia from a distance. If not, Lydia, I'm happy to schedule like Zoom office hours and whatnot to work with you. Thumbs up. Okay, this is recording right there.
Well, I clicked. You don't trust me?
No,
Why?
because you're not trustworthy.
That's not true.
And your face is ugly.
You don't have a beard.
So, any other questions or comments before we get started for today? Okay, and in that case, Lydia, I said that because he was calling my face up. Several people were asked one day to test the following hypothesis, that all odd numbers greater than 1 are prime. Mathematician goes first. 3 is prime, 5 is prime, 7 is prime, but 9 is not prime. Therefore, the hypothesis is false. The math grad student says 3 is prime, 5 is prime, 7 is prime. Therefore, by induction, every odd integer greater than 1 is prime. The physicist says 3 is prime, 5 is prime, 7 is prime, 9 is not prime, 11 is prime, 13 is prime. Takes 5 out of 6 experiments to support the hypothesis. Clearly, it must be true. The computer science student says 3 is prime, 3 is prime, 3 is prime, 3 is prime. They need to work on their code. The biologist says 3 is prime, 5 is prime, 7 is prime, 9, more research is needed. A psychologist claims 3 is prime, 5 is prime, 7 is prime, 9 is prime, but tries to suppress it. Finally, the politician says some numbers are prime, but the goal is to create a kinder, gentler society where all numbers are prime. And with that, let's get back to it. So last time, we looked at the minimal polynomial of some element in a field extension of field K. So we're assuming we have some field extension L of K, and that alpha is some element in L. Last time we proved that if alpha is the root of any polynomial in K, then there exists a minimum polynomial of alpha over K that is unique, which is the monic irreducible polynomial in K of minimal degree that has alpha as a root. So for instance, we're looking at R over Q. We want to look at square root of 2. Square root of 2 is an element of R that is not in Q, but what would be an example of, what would be the minimal polynomial that alpha satisfies over Q? In other words, what would be the polynomial whose coefficients are rational of minimal degree that has alpha as a root? So we could say m of x in this case would be x squared minus 2. If I were to give you square root of 2 plus square root of 3, there'd be a little bit more algebra involved, and that would be a homework question, which I'm not going to spoil. But you would get something of degree, spoiler alert, 4. If I were to give you alpha equals pi, on the other hand, what would be the minimal polynomial of pi? Lincoln?
Well, actually,
Shut up.
since since what Q bracket alpha is equal to since Q bracket pi is equal to Q since Q parentheses pi is equal to Q parentheses x.
They're isomorphic. They're not equal, but go on.
Yeah, right. Anyway, it satisfies the first criterion in the big snazzy theorem and not the second.
Yeah. So we said not every element in L necessarily has to have a minimal polynomial. Pi, for instance, does not, as over Q, which proving that is non-trivial and actually takes some doing. And we're not going to prove that in this class. We're going to prove some elements do this. In fact, we're going to prove most elements in R, dare I say, don't have minimal polynomials over Q. But we're not going to prove any specific one. But if you do have a minimal polynomial, then the minimal polynomial has all these nice properties. Like for instance, with x squared minus 2 and square root of 2. We said that if f of alpha is 0 for f some polynomial over k, that's going to be f has alpha as a root if and only if f is a multiple of the minimal polynomial. We said that if f has a minimal polynomial, then the field extension of k by alpha is actually the same as the polynomial ring of alpha over k. So in other words, the ring of polynomials is equal to the ring of quotients of polynomials of alpha over k. And finally, if you know what the minimal polynomial is, then the degree of that minimal polynomial must be equal to the degree of the field extension, extending k of alpha over k. And in fact, that's why we call this the degree of the extension. Degree actually refers to degree of minimal polynomial. So that's where we left things off last time. And what I want to do today is I want to look at under what circumstances does an element alpha have a minimal polynomial, and under what circumstances does it not have a minimal polynomial. And that is going to be the difference between algebraic elements of a field extension and transcendental elements. So let's talk about those.
I gotta tell the provost about this one.
Yeah, you do that. So, first thing, we're going to say that an element alpha is algebraic over field K if alpha has a minimal polynomial. and transcendental if it doesn't. So let's write that
We're
down.
just defining it after that.
Yeah, I know, jumping right to it. Well, we've already talked about, well, we already, in the last packet and on before the break, defined all the things that are needed to define algebraic and transcendental, so let's hop to it. So here we're going to have K is a subfield of L, so L over K is a field extension, alpha some element in L. And we say that alpha is algebraic over K. If alpha has a minimal polynomial, and it's going to be transcendental otherwise. Have minimal polynomial. So for instance, if we wanted to look at, I don't know, let's have some fun. Complex numbers over the rationals. Which elements would be algebraic in this extension? Which elements would be transcendental? So, what would be an example of an algebraic element in this extension? Jonah,
Root 2i.
root 2i? Which, I'm just going to split that up and say root 2 and I would both fall in the algebraic column. And we're going to show later on the product of algebraic elements is algebraic. In fact, the algebraic elements are going to form a subfield that gives us an intermediate field in this extension. We'll show later on. Yeah, square root of 2, algebraic over q. That's minimal polynomial, x squared minus 2. I, also algebraic over q. X squared plus 1 would fall into that category. Literally any element in q would also be technically algebraic over q. Why? Because it'll just have minimal polynomial of x minus a over b. Tans?
A transcendental number for this would, well, we haven't proved it yet.
Is there anything you believe to be a transcendental element of this extension?
Pi.
What?
Turns out pi is transcendental over q. What else? Isaac? That's another famous one. Even harder to actually prove, but can be shown, but is known to actually be transcendental. Doesn't have a minimal polynomial. Jonah?
Pi plus 1.
Pi plus 1. In fact,
Pi plus
I'll do you one better. A over b pi plus c over d.
Which one are you gonna say?
Pi plus I.
Pi plus I. That'll be transcendental.
Pi squared.
Pi squared.
If we take any rational polynomial or any polynomial with rational coefficients and evaluate it at I, it feels like that should be transcendental.
In fact, it will be. And that's a direct consequence of pi itself being transcendental. Any rational polynomial of pi must also be any other than 0.
1/2 factorial.
What's that? Is that like square root of pi over 2?
It's also basically another function of pi.
Is that square root of pi over 2? Let me forget that.
It's transcendental, that's all I know.
I'm not writing that. But yes, whatever it is transcendental.
As I recall, pi to the pi to the pi, but not necessarily pi to the pi to the pi to the pi.
Is that the case? I haven't actually heard that one.
I thought pi to the pi was I thought there was like an alternating pattern.
You get the idea.
Would the golden ratio be algebraic?
Yeah.
Yeah. Yeah, it's 1 plus square root of 5 over 2.
Yeah.
Multiply by 2, subtract 1, square it, you get something rational.
Yeah. Let's see, what about?
It's just
what
fun to
about
have a
phi
number
too?
that has a name, like pi and e have names, that isn't transcendental.
What about
I.
Okay, I also.
I was gonna say I's a famous one. I's interesting because this are all real numbers, whereas I is not. You could have elements in here that are non-real numbers that are algebraic, or ones that are transcendental. Pi I, for instance, would fall into the transcendental category.
Is 5 to the 5th power transcendental?
Yeah, fee fi fo fo. Yes, I believe so.
Oh, okay.
Pi to the pi. Yeah.
No, 5 to the 5.
Let's do a different way.
Oh. Yeah.
Crunchy.
What if that's your field extension?
Ooh.
How do you feel about that?
Ooh.
Oh, how do you feel about that?
So because well, then 1/2 factorial.
So what would be some other algebraic and transcendental things?
1/2 factorial.
1/2 factorial, I'm pretty sure would be algebraic in this case.
Yes.
Yeah.
That's why I said.
I'm just going to go with square root of pi, for instance.
Oh.
Yeah.
That's not fun.
So what would be the minimal polynomial of square root of pi in this field extension? Eleanor?
X squared minus 5.
X squared minus 5. Pi itself is not an element in Q of pi. This will give you all. This will give you like pi squared, pi cubed, pi to the -1, pi to the -2, all integer powers of pi. But it won't give you pi to the 1/2, for instance. So square root of pi is not in this field, but it is still a root of x squared minus pi, and hence will be algebraic over this field extension.
A transcendental number of this field is still E.
It's still E, is it?
We don't know.
No, because we don't know if e times pi is transcendental.
Oh yeah, that's right, we should.
Probably transcendental, but this is actually an open problem.
Probably. It's probably transcendental.
We don't actually know if E be is E transcendental or not in this field.
Can we get any fractional power of pi as an algebraic?
Sure. Yeah, because pi to the a over b, you just take is going to be a root of x to the b minus
Pi to the a.
pi to the a. Pi to the a over b will always be a root of that, no matter what your b is. Well, don't divide by 0. Yeah, so pi to the a over b for any a over b in element in Q.
With e not equal to 0.
Well, but if
Well, if b not equal to 0 is implied by a over b is an element in Q. If b happens to be, if a over b happens to be an integer, then you actually get an element in Q adjoint pi. But in that case, you just have a minimal polynomial that's linear of degree 1, x minus whatever power of pi you're looking at. But yeah, E is an open problem. Anything that's in this field already, so any rational number will be in the algebraic column. But depending on what your field extension is, what your base field is, as well as what your extension is, that can determine what ends up being algebraic and what ends up being transcendental. For instance, we are certain that E falls into the transcendental column here, but here it's still like we strongly suspect that E is transcendental in this field extension, but it is, but nobody's been able to prove it yet.
Do we have any transcendental numbers that we know of in this field?
That's what
Well,
that's
Oh,
like
in the field you
In
mean?
that field, yeah.
No.
He's
No,
asking
what's
us-
transcendental?
What's transcendental?
Oh,
Over
do we
that.
know of
Over
anything that's
that.
transcendental? Gotcha.
Well, we know that there are lots
I don't
of
know.
them, we just don't know how to write them down.
It's true.
We can prove that
Wait,
there's a lot.
what if? Oh wait, I think I got one. 3.151, etc. Just change one of the digits of pi. Oh wait, never mind.
That is definitely going to be algebraic.
If
What
we
about,
want.
wait, what about?
Oh.
Say what?
Change all of the
That
digits.
you would have to have some sort of method.
If you increase them all by 1, then you're increasing pi by 1.1 repeating, which is increasing pi by a rational number, which is algebraic. Anyways, you all get the idea. So I have a question. So when mathematicians talk about algebraic and transcendental numbers, they often just talk about, is this an algebraic number or is this a transcendental number, without specifying what the field extension is. What's the base field when you're talking, if you don't specify? It's going to be Q. If you don't specify, like, is this algebraic over blank, it's usually assumed to be Q.
Is that because of Galois and Galois theory?
Not really. Well, I wouldn't say it's a direct result of what Galois does, but they are strongly related. Yes. So let's do a quick theorem. Turns out, one way we can tell if an element is algebraic or not is to just look at the degree of the extension that it generates over K. Turns out we can say alpha is algebraic over K if and only if the degree of the simple field extension K of alpha over K is 1.
Hey, I use that in
Yeah.
Really?
I sure you improved it.
No.
I'm gonna say
I just used it as a given.
Oh, okay. I'm very curious as to where you use this, but I guess I won't spoil that for myself if I can.
I remember that we were talking about this, and I was like, I don't remember
I didn't
proving.
end up.
I don't remember proving that yet. And now you're about to.
So it turns out this is
Why are
actually
you killing your eraser?
pretty straightforward to prove. That if alpha is algebraic, then it has a minimal polynomial, and so the degree of that extension is just whatever
See,
the
that's
degree
the
of that
fact that I
polynomial
used
is.
on the homework.
Yeah. Oh yeah, that's totally fine. I expected you to use that. So if
I didn't. It's different
alpha
voices.
is
I
algebraic
didn't use this.
over K, then alpha has
No,
a minimum polynomial, and of x.
the snazzy pretty much for everything. Yeah.
I mean, pretty much. It does a lot for you.
Yeah, it does.
I mean, I know I used it a lot on homework personally. Equals the degree of m, which is fine. Okay, there's forward direction. So how about the backwards direction? It's a little bit trickier. If the degree of the field extension is finite, then how do we know alpha is necessarily algebraic? Or, equivalently, if alpha is transcendental, how do we know the degree of the field extension has to be infinite? Lincoln, you look like you have an idea.
Well, no. Now that I think about it, it was only going to work for a specific case of Q.
Alas.
Can we look at K adjoint X? The degree of K adjoint X with K?
What's that degree going to be?
It should be, right?
So, you're right. Why?
Because they're isomorphic by the first part of it.
Oh, because you
Yeah.
would like them to be in order to be able to prove it.
Yeah.
Turns out you're right.
Okay.
If alpha is transcendental over K, then we know from Big Snazzy theorem, we know that K adjoined alpha is isomorphic to that And Eleanor is correct that the degree of this extension, well, technically this isn't a field extension, but we can, dang it, now this is taking us a different direction down what I wanted to do. Actually, no, let's do this a little bit differently because I don't want to get into deep dive. How does this behave if it's not a field? So if alpha is transcendental over k, then I think we can show directly that this thing has to be infinite. How do we do that? Let's construct an infinite basis for k of alpha as a k vector space. So how do we do that? Well, turns out we can form a basis for k of alpha as a k vector space by, we could take 1, we could take alpha, we could take alpha squared, we could take alpha cubed, we could take etc., etc.
Oh yeah, my favorite element.
Ah yes,
Etc.,
the old
etc.
dot dot dot. Turns out that's a linearly independent set.
Why is the double up in so many sets?
What's what?
Why is the ellipsis in so many sets?
Yeah, I know.
Because laziness is linearly independent over k, I claim. So why is this set linearly independent?
Didn't we prove that it is last time?
Did we?
I think so.
I think we proved that it's linearly, that if we went up to alpha to the n minus 1, then it's
Oh,
linearly
right,
independent in the
right,
case where
definitely.
alpha has a minimum polynomial of degree n.
Well, they're each alpha multiples of each other, and alpha is transcendental, so.
Yeah, because if they were linearly dependent, we could form some polynomial of them that would come out to 0. And in that case, alpha would be a root of a polynomial over k, making it algebraic and not transcendental. Since otherwise, alpha would be the root or would be a root, I should say, of some non-trivial a naught plus a sub 1 alpha plus dot 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 plus a sub n alpha to the n.
No, I'm writing it in summation form.
Okay, go for it. I don't care. Making alpha algebraic, not transcendental. Like it?
Should we have had negative powers of alpha in the basis because we're looking at
True,
parentheses?
if we were looking to actually form a basis.
But this shows we already have the elements.
But we already have infinitely many linearly independent elements. Any basis is going to have at least as many elements as this linearly independent set using linear algebra trickery. Hence, any basis has infinitely many elements, and so the degree of the extension would be thus, any basis for k of alpha over k must be infinite. Hence the degree of the extension is infinity in that case. And that proves the backwards direction. If alpha is algebraic, then the degree of the extension is finite. If alpha is not algebraic, then the degree of the extension is not finite. Any questions or comments about any of this? Other than Dr. Gerstle, why do you like dot 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 so much? That would be very valued. Okay, so in that case, let's move on. Turns out, not only can you can not only just talk about individual elements in a field extension being algebraic or transcendental. You can also talk about the field extension itself being algebraic or transcendental. So let's write that down. Turns out you can call a field extension algebraic if every element in the extension is algebraic, and it's transcendental if at least one element in the extension is transcendental. So we can say L over K is algebraic extension if every alpha in L is algebraic over K. Transcendental extension otherwise, if at least one element in L is transcendental. So with that in mind, what would be an example of an algebraic field extension? And/or what would be an example of a transcendental field extension? Isaac, give me one.
K adjoins square root 2 plus square root 3 plus square root 5.
What's your K?
Or sorry, Q.
Over Q?
Yeah, over Q.
Okay. What would which column would that fall in?
This should be algebraic.
I'm just gonna write Q of square root of 2 plus square root of 3 over Q.
Yeah.
Are you sure about that?
I'm not sure. No, I have not proved it. I believe so.
You're correct, it is. Turns out, if it's just a simple extension, then this single element being algebraic over Q is enough for the whole extension being algebraic over Q.
Yeah.
Not too hard to
You
show.
must deal with commas and there'd be a
I shudder to ask, Lincoln.
C over C is algebraic.
I mean,
I'll generalize that to say any K over K is algebraic. Because every element, I mean, that is an example that's worth mentioning, I think. Any field is algebraic extension of itself, because any element in the field has a minimal polynomial of degree 1. Alpha is always a root of x minus alpha if alpha itself is in your base field.
We were debating earlier R over Q adjoins pi if that was algebraic or transcendental.
Alright, how about this? I'm going to give you a list of them. You all take a couple minutes and determine which column each thing in this list falls into. Sound good? Got an activity time. Alright,
We need him to sing on
that
the
one. Do that one.
Separate the moment's voices.
Alright, that's enough out of you.
spicy.
What?
Oh,
Oh boy, I like this one.
my
Alright, calm down, kids.
Holy moly. Oh my goodness.
Alright, get to work. Which column do each of these fall into? Talk to each other.
Oh,
So,
And don't
which
just
one
make
is
words
algebraic?
voice. Some
I wonder which is algebraic.
Yeah.
So, R over Q is definitely transcendental.
Yeah.
C is probably algebraic. And C over Q is the transcendental here.
So the last one is
Well, we were debating whether it's
Yeah.
or not.
Oh, right, we don't know.
There may be a trick question in here. Let me rephrase. I may not know the answer to all of these.
And then we just put you on the problem and make you deal with it.
I
Very
don't
true.
Very
You Zima 2 adjoined I over Zima 2.
Adjoined pi.
Is that adjoined I? Is that adjoined
No, that's
joint.
No, it's adjoined I. It is Zima 2, right?
Zmod 2 adjoined I over Zmod 2.
Yes.
it's just
Sometimes
like
I will
pi
get mixed up
Zero
mod
is
or
one,
2z, and I know this is mod, but
and 1 plus
for a second I was like,
Well, 2z is not a field, so it has to be z mod 2.
No.
that should be Algebraic.
No,
It's
that's
zero or
the only.
Can you do x squared plus y?
Oh wait, but then you do the square roots, and then pi squared, and then you do pi cubed, or you could get root two
You can find the minimum polynomial.
because
So, that's just gonna give you
exponents
a
are actually
Yeah. Are they field extensions?
What?
Z mod 2.
Z
No,
mod
no,
2 is
no,
not
adjoint square is not.
Because-
No, it is, and it is, and it's finite.
So what's the consensus?
Because remember we showed in the earlier class that k parentheses alpha if it's finite. Which does imply that that is not.
Oh,
Is
That's interesting. Yeah, that's true, that's true. If writing that, if it's a field,
But then you need, because 2 pi is just gonna be equal.
if
What is 2 pi even equal to, or pi, you have pi and 0,
2 pi is equal to 10.
or 1 plus pi.
Pi over 2 is equal to pi over 4.
Right, so what even elements you have in that? You have 0, 1, pi, pi plus 1, pi squared plus 1.
is Z mod 2 adjoint pi with square brackets even a field?
Oh, that's true. That's true. That's true. I should try and A, not give away the answer, and B, actually make sure these are fields.
Oh, goodness. Well.
I think it's just algebraic. I think that's what I think too.
Do you think the
And then I think this one is, the last one is.
couldn't you?
Let's give it another minute, and then we'll come back together.
Have insert 1 in there. It wouldn't be odd.
I think.
no, because
No.
it still has the root, it still has the root.
Why would its root also be just 1? Would it be
big
both?
enough to cover.
Because if you just put 1 in there, it goes to 0.
Yeah, one is also a root.
Right? So both of them would be roots technically?
Yeah, it just needs one.
Oh,
That's
that's
agreed,
fair.
it's agreed too.
Yeah. That's kind of
And I think for the other one,
Yeah,
it's
yeah, the powers are
you don't do
independent
anything.
of the Z mod 2.
Q
It's
and
just
pi
what you're
and
allowed to
E
plug in
over
for
Q.
X is severely
They're
restricted.
either the same, they're, we don't know, because we were talking about that earlier.
Importantly, I mean,
Or the coefficients.
And the coefficients, yeah, but not the powers themselves.
importantly, like, within the actual
polynomial in
polynomials are just weird, right? Since I isn't even an element of Z mod 2, like, it doesn't even count. I don't even think it has the algebraic.
What would that it would have to be.
All right, that's enough. Let's come back together and discuss.
Technically, you just have one.
So I want to put this to a show of thumbs. Thumbs up for algebraic, thumbs down for transcendental. Y'all ready? C over R. R over Q. C over Q. You can actually prove this one using these because the degree of this extension times the degree of that extension should come out to the degree of that extension by something we proved a couple weeks ago. And if you claim this one is infinite, which you are claiming by saying this is transcendental, then this one must necessarily be infinite.
Thumbs up.
Algebraic. Still use x squared plus 1. This one. And the last one. So that's the same as asking is E algebraic over that extension, and then that's the thing that's
Yes,
unknown.
that's what I did.
No, yeah, it's
No,
it's quantum.
it's one that's very slight.
I'm putting a question mark. I'm putting a question mark there for unknown.
See, but that's just guaranteed.
Probably transcendental, but it's not. But it's still not proven one way or another. So, in general, if you have a simple extension, you just have to check if the simple thing you're extending, the alpha you're extending it by, is algebraic or transcendental. That'll tell you whether you have an algebraic or transcendental. Ooh, maybe I should have an example.
The first one is a simple extension. You just join.
This one is a very simple extension because C is R joined I, and I is algebraic over R. Therefore, C is algebraic over R. This one is not a simple extension whatsoever.
Hence the transcendentalness of the extension.
Well, no, that doesn't make it non-transcendental. Like you can have non-simple extensions that are still algebraic.
Can you give an example?
Yeah, just to join any two elements
Oh.
that are algebraic.
Oh, okay.
Like it'd be like if I wanted to take Q adjoined N. That's not a simple extension. Pretty sure. And
Huh?
No, it
Wait,
isn't.
no.
How are you gonna get negative square root of, or negative root of -2, which is what you need to get I?
Q adjoined I consists of rational numbers of the form a plus bi, which definitely does not include square root of 2. So adding square root of 2 is on top of I. Yes, I'm pretty.
Okay.
This is not a simple extension.
Right.
Well, that's true. That's true. Could this be generated by something like I plus square root?
Yeah.
Alright,
that's
that's
what I
not
was-
the
That's
thing.
what I thought it
Yeah.
might be generable by.
Because they're both.
Point is, doesn't have to be simple to be algebraic. This I can confidently tell you, these two are not algebraic extensions. Are not simple extensions.
Agreed.
What if we take only the algebraic subfield of R over Q?
Good question.
Just be.
Let's do that. And that
Seamus.
leads nicely into our next page.
Or no, I guess it would include square roots too.
No,
It's wait. So is the degree of R?
Turns out you could take the set of all algebraic elements of L over K, and that'll actually give you a subfield.
Oh wow.
Oh, you can say.
It's a fancy A, Math Cal A. How about that?
Math 1A, how do I write this thing?
Math Cal. /MATHCAL.
Awesome.
And then in brackets A.
And then it will magically turn.
It's not.
Here's one
No.
for you.
It's
We're
a
gonna,
whole A.
Yeah, on your paper.
given
A is like this.
given some field extension L over K, we're gonna let fancy A of L be the set of elements in L that are algebraic over K. Then it's going to turn out to be the case that a fancy A of L, in other words, the algebraic elements of L over K, form a subfield.
So does this imply that the dimension of L over K is not prime based on the homework?
The dimension of what now? L over K?
Yeah.
Not necessarily, because you could have that like this is equal to all of L, or this could literally just be K. In which case, one of those could. There's no reason why the degree of either the intermediate subfield extensions couldn't be 1. In other words, and that's subfield of L satisfying. K is a subfield of Watchadoodle. It's a subfield of.
Now I know his name.
The old Watchadoodle. Now it's the algebraic elements of L.
So then.
So what's the fancy T for the transcendental? If you have a.
Math LT, presumably.
Oh. I don't like that now. I don't want there to be a fancy T.
Well, fancy T. There is no fancy. Well, what?
SpongeBob.
The set. I'll say this: set of transcendental elements doesn't form a field.
Yeah.
For instance, it does not include a zero element.
What if you do include a zero element?
Adjoins
Then it's not transcendental!
Then,
Oh wait, but ignore that part.
then that implies the original base field doesn't have zero, in which case it wasn't a field to begin with, so that can't happen.
Oh.
Someone Lincoln.
So if L equals K, then what does A of L equal?
Jonah, what was your question?
I guess what do we call it? A.
The algebraic elements of L.
Okay, that has no.
The algebraic subfield of L is another way.
Right, but that field has no algebraic things outside of it. I mean, every it has no algebraic things that are on this within.
The ham sandwich there.
Yeah, the ham sandwich there.
You mean anything? Are you trying to say that anything that's algebraic over this also has to be algebraic over that?
Yes.
That's an interesting question. Turns out the answer is yes. Mainly due to the fact that polynomials of polynomials are still polynomials. So, let's see if I can prove this. Gee, I hope so. Can you prove it?
No.
So this is actually fairly straightforward, this subset thing. So really, the thing that we need to prove is that that the algebraic subfield of L actually is a field. That this forms a field. So how do we prove something's a field? Or is a subfield?
Inverses?
Inverses.
Given that we already know that it's a subring, right? Do we know it's a
Do
subring?
we know it's a subring?
Or do we just know it's a subset?
I'll give you a hint. If we know it's a subring, that's enough to guarantee it's a subfield.
Okay, so we know it's a subset. So we need to prove it's a ring and then to prove it's a field, and that just means a bunch of inverses. And
Well, so we need two things to prove something. To prove something's a subfield here.
subfield test.
What's a sub? What is a subfield? Do we have a subfield test?
Subring test.
We had a subring test.
And when you're applying it to field, it has to.
Yeah. Basically, we can show that this forms a subfield by showing that it's closed under division and subtraction.
Yes.
So we're going to do the subtraction. I'll leave division up to you all.
Maybe the
Oh.
one step subring test.
So let's suppose
Nah.
two-step subring test. So let's suppose that we have two elements, alpha and beta, that are elements of this that are both algebraic elements over K. And our goal is going to be to show that alpha over beta and alpha minus beta are both also elements in this thing. Well, then what do we know about alpha minus beta, for instance? Well, we do know that it has to be an element in some field extension, namely K adjoined alpha and beta, which is equal to K adjoined alpha adjoined beta.
Oh,
No.
goodness.
Oh.
Meaning we could write this as a double simple extension. We can do a simple extension, extend by alpha, and then extend by beta. That means the same thing as extending by alpha and beta. And then what's the degree of
Set of brackets.
What?
Those are some beefy brackets.
I think we could say that since beta is algebraic over K, beta must also be algebraic over any extension of K. Because by extending K, you're just adding in more possibilities for polynomials that beta could possibly be a root of. So if beta is a root of some polynomial just over K, beta is also going to be a root of some polynomial over elements of K and then some.
Use the same minimal polynomial.
Hence, we know two things are finite. We know this, K adjoining alpha, adjoining beta
Why is it what?
over K.
Oh, it's fine.
Oh.
This looks like my homework.
Oh.
There's no need for that extra.
And
There's no need for this violence against
Yes,
our
there is.
K
There is, unfortunately.
and K adjoining alpha over K are both finite.
No, the inside.
Those are
Would you agree with everything so far, despite how scary it may look?
That looks great.
Oh, thanks. Does it?
Yeah.
That's actually not too bad. I'd say so myself.
You can just keep doing threads.
I've done
You could just keep doing parentheses.
No.
So if that's an algebraic extension and that's an algebraic extension, or meaning if that's finite and that's finite,
And the product is finite.
then the product is finite, meaning this thing over K has to be a finite extension,
I love it.
or algebraic extension, excuse me.
And then delta, and then epsilon.
K of alpha and beta over K, which is equal to the product of these things. I'm just going to say K of alpha and beta over K of alpha times alpha over K is finite. Hence, K adjoined alpha and beta over K is algebraic. By our theorem from earlier today. Everyone on board so far? Well, if this is an algebraic extension, then every element in this extension has to be algebraic over K. What do we know is an element in this extension? Well, what do you know? Take alpha minus beta. And as an element in this, alpha minus beta is algebraic over K. So in other words, alpha minus beta has to be an element in this fancy whatchamacallit. Is that what I called it earlier that you all thought was funny? The algebraic element.
Can we just call it Al?
You know what? I'm okay with it. Let's call it Al.
Or O. But Al is better.
I like Al better.
I like Al better.
Any questions or comments about that? So how about alpha over beta? Assuming beta is non-zero.
Isn't that also just a element of K of A and B?
If this is a field, it better be.
Yeah, like I don't think it.
Alpha over beta is going to be an element in here by the same logic. And hence, A of L, hence Al is a subfield of L.
Yeah, I like that.
There we have it. Since
As
as the prophecy is foretold, yes. Since Al is closed under subtraction and division, we have pick your favorite subring test from Math 410. You could use that to show that we get a subfield here. Questions, comments, concerns? How are we doing? Oh, we're doing great. All right, now, who's ready to do some real analysis? Well, then you should know all about cardinality, shouldn't you?
Oh yeah.
So, Eleanor, riddle me this. What can we say about countable unions of countable sets? They're countable. What about countable unions of countable unions of countable unions of countable sets? Also countable by the same argument, right? Congratulations, Eleanor, you just proved the next theorem.
Here's your math baby. A.
So, this is where I asked you all, I think before break, like, who's seen cardinality before? I'm not going to ask you anything that requires advanced cardinality, things on like exam or homeworks or such. But it turns out you can make, I mean, if you all really want, I can. I don't actually know what I would ask, but we can actually use some kind of a sneaky cardinality argument to show that the field of algebraic numbers, meaning meaning A of R, is a countable set. Nope. Algebraic real numbers over Q.
I forgot which shapes.
Algebraic numbers. And again, since we're not fine. Fine, it's really supposed to be something like aqua, because it's really, or ac, because it's really more like the algebraic elements of the complex numbers, is really what we mean.
But R is more fun to say.
But R is more fun to say, I agree. And either one is going to be countable. technically though, here's one for you. Figure out how to tech that one, Emily Rose.
What? No, that's just math BBA, right?
Yeah, you're right, it is. Is
The library math BBA for you.
so in other words,
LaTeX.
the size of the number of so here A, by the way, just as a side, as I kind of mentioned earlier, is fancy A of the complex numbers for the field extension C over Q. So there's only a countably infinite number of complex numbers that are algebraic over the rationals, in other words.
Oh, this is what we were talking about proving earlier, that there's a lot of transcendental numbers that we don't have names for a lot of them.
Exactly. That's why we say most real numbers, most complex numbers
In fact, by
are
probability, it's even
algebraic.
almost all.
In fact, yes.
By probability, the probability of landing on an algebraic one is 0.
Depending on your selection.
Well, assuming who completed random selection. So let's prove this. Turns out this basically just uses countable unions, countable sets over and over. So first of all, let's fix for some fixed n, how many monic polynomials of degree n do we have? For fixed n, the number of monic polynomials of degree n with coefficients in Q how many rational polynomials can you have that go up to x to the n?
It should be coefficients in Q.
You wrote coefficients in n.
So I did. That's embarrassing. I managed to confuse my Math 105 first class this morning for a good 3 minutes. And I couldn't figure out why until I realized I had written natural number instead of even. That was embarrassing.
Up there?
Say what?
Was it up there originally?
No, it was for something we were proving. I forget. Something like product of even numbers is even, I think. All right, Eleanor, you're in real analysis. What is this?
It should be the number of rational numbers times n minus 1.
Rational elements to the power
Power of n minus 1.
of n.
But it's mine. So the first.
But there's a constant
There's a
term, so there's
constant
n
term.
plus 1 terms in it.
Right. Forgot about that.
Either way, it doesn't matter.
Because that's countable.
That's still just the cardinality of Q,
Yes.
i.e. countably infinite.
Yes.
Wait, you're telling me? Oh no. Single bars mean another thing?
Well,
Wait.
this just refers to cardinality of the set, like number of elements in the set.
The better notation is just a hash symbol, pound symbol, and then
Okay, Mr. CS, yeah, you could do
No.
that.
No.
Why?
I'm using the notation I've learned used all my life. And by all my life, I mean, when did I first learn about cardinality? About 15 years ago.
didn't have Vsauce.
14. What's that?
You didn't have Vsauce to introduce you.
I literally had the textbook author to introduce me. So, every such polynomial can have, at most, n roots in C, excuse me. Hence, at most,
Wait.
blank.
Can it have, doesn't it have exactly n roots in C?
We could have repeated roots.
Oh.
Or maybe I should say n distinct roots in C. Hence has at most blank roots of monic polynomials of degree n over Q exist in C. Ooh, that's hard to write. At least this many roots, this number of roots of monopolynomials degree n over q exists in C. Yes, so what do we put in the blank here? If we have cardinality of q, number of monopolynomials, and each of those polynomials can have at most n distinct roots, how many distinct roots are we allowed to have in total? Who knows their probability or their combinatorics? If there's cardinality of q number of things, and each of those can have at most n things, how many sub things can we have in total? N times cardinality of q.
Which is just the cardinality of q again.
So we're just using that you can raise to the power and multiply infinity by whatever and it stays the same.
For countable infinity.
Okay.
Yes. Well, yeah, and for a size of infinity, yeah. A size of infinity to the n power doesn't change the size.
Yeah.
Ditto with multiply. Now, if you were to, for instance, take n to the power of cardinality of q, that would be much, much bigger. So, we have a countable number of roots of monopolynomials over q in C of some fixed degree n. Now we just need to take the union over all possible n. So in other words, we need to combine these over all possible polynomial degrees. The union then over all n any natural numbers. Why did I write positive integers? I'm sticking with it. Gives blank elements in C at most that can be roots of monopolynomials in Q.
Zero, isn't it?
What?
Does C plus equal 0?
No,
it's
not. That's why it's
We just used it to do
Yeah.
just n vectors.
All right, so if we have cardinality of Q, roots of monopolynomials of degree n, and we're taking the union of all of these possible roots over all polynomials of degree n, what's the biggest that this could possibly be?
It's still going to be cardinality of q.
It's going to be cardinality of n
times the cardinality of q.
times the cardinality of
Which is
Q,
still going to be equal to cardinality of q.
which is still equal to cardinality of Q. But what do we know about elements in C that can be roots of monopolynomials over Q? That's precisely the same as the algebraic elements. Yeah, sure, whatever, that's fancy enough. There we go. There's some analysis for you mixed into Galois theory. Not really analysis, more just general countability. So that's a class you typically learn about that. Basically, it basically comes down to what Eleanor said earlier. An accountable union of a countable union of a countable union of a countable set is countable. Of countable sets is countable. Questions? So what can we immediately say as a corollary to this? Well, if there's uncountably many complex numbers, and there's a countable number of algebraic numbers,
Transcendental numbers exist.
transcendental numbers exist. How about that? In C over Q specifically.
And doesn't it also follow that there are uncountably many?
It does follow that there are uncountably many. But I like the way the book wrote it. In the book it just says transcendental numbers exist. So I mean that is a corollary to this.
Numbers exist.
Proof? Well, now we know that since the cardinality of the complex numbers and the cardinality of the real numbers, quick, what's the relationship between these two cardinalities?
Equal.
They're equal. Very good. Is much, much, much bigger. Well, it's not that much bigger. Much bigger than the cardinality of Q, which, as we've seen, is equal to the cardinality of or no, not that A, of this A. Now it's just not Al. So what is this greater than symbol? We know that the complex numbers minus the algebraic numbers. I'm not used to handwriting this symbol, so I'm not very good at it. Whereas with the Z for the integers I've done a million times, is not empty. And I'll write in parentheses. In fact, it's transcendental.
How's transcendental cardinality, or is it just
Is uncountable is what I meant to say.
Oh.
I was gonna say yes. That's I'll put a sad face because I screwed up right back.
C minus A is uncountable.
You'll never be able to count every single one.
Try as hard as you might.
Well, even countable infinity.
I was gonna say countable infinity, you might have
Even
trouble.
finite are a little bit difficult for me, let's be honest.
I've seen Eleanor's homeworks. Counting to 4 can be a challenge.
You want me to count? I'm sorry, you want me to count point blank?
You want me to count? I'm in a high level math class. I'm already
I have a
on
que-
that. I don't need to count.
I have a question for you all. Does anybody know what was the first number that was proven to be transcendental?
I don't even know what the first number is.
What? I don't understand what you just said.
Oh,
No.
Maybe.
It's not pi. It's not E.
wasn't it some multiple?
Square root of 2.
Oh.
What is this gobbledygook?
Oh, what?
Oh.
That was
yeah,
the
we
first
don't
one?
That was the first number proven to be transcendental.
Yeah, but what does it look like?
What?
What's the
That's what it looks like.
decimal? Well, no, I'm like, no, but what, like, that's so unsatisfying. And the dot dot dot?
Undo the undo.
You can work it out yourself, Parker. It's not that
Oh, no.
complicated a number at the beginning.
I don't know what it counts.
Anybody know who came up with this number and proved it was transcendental?
The smart guy.
Gauss?
Gala?
Hint. Hint. Big name in complex analysis.
Cauchy.
Not that big. Not Cauchy.
Weierstrass.
Schwartz. No.
Anyone German, maybe.
Christoffel.
What was the first name you said, Lincoln?
Stroopwafel.
Oh, right.
Hint. Where is Dr. Gerstel from?
Yeah, I was right, Leoville.
Leoville. Yeah. This is called Leoville's
That was
constant.
that was my first guess.
Oh, was it? I didn't hear that one.
Yeah, because it's a Leoville number. Right.
It's a Leoville number.
I didn't know how to it. Negative, yes. It's good.
Most famous for Leoville's theorem, which is the theorem that the complex functions that are differentiable over the whole complex plane and are bounded must be constant. Take complex analysis. It was actually much, much later that pi and E were proven to be transcendental.
Wait, proven in 1844.
It's proven in 1844.
Well, no way.
That's pretty quick.
That's a good year for the world.
How about that? I didn't know that, but that's what Wikipedia told me.
I think a sponsor would love to hear that.
So true.
We were founded at the same time as the.
I didn't know.
Just
I mean, I didn't know what the first transcendental number was, but the book hadn't decided, and I thought, oh, that's neat. I'm going to look up more.
We need a scholarship named after this guy or something.
Yeah.
Get the logo.
1844 society.
Leoville.
Only for students from Louisville, Kentucky. I could already give it to my
I know
hometown.
some of those, and they're not even math
We
majors.
decided to major in
Yeah, I was like, There's one other math major from local my year at Kenyon. I don't know where he is now. It's about the same size, so still. It's only like 1,600.
Wow.
Maybe like, yeah, it's about the same size. They have much nicer. I'm sorry, I'm not there. Any questions or questions or comments? Turns out what this means is that if you were to randomly choose a number out of a hat containing all real numbers, A, wow, that's a big hat, and B, you would have a probability 1 of choosing a transcendental number, and probability 0 of choosing an algebraic number. There's many more transcendental numbers than there are algebraic numbers.
I believe in alternative analysis. The
Well, you
numbers
said
are
all.
really, really small.
Oh.
Yeah, tell Dr. Cipher about this one. I'm just curious what he has to say. Hey.
Sorry, where were we? He's like, so the first.
I don't know, just tell about pulling transcendental algebraic numbers. I'm curious if Dr. Cipher believes in any transcendental numbers.
Probably not.
Oh, no.
How do you get around? Would he believe in computable ones?
I'm not I think he believes in some, but not all computable ones.
Does
really?
believe in anything you can.
Well, he only believes in a finite number of numbers, so
Yes, he believes in any number you can physically represent.
I'm pretty sure.
And since there's only a finite number of atoms in the universe, for example, that's how many numbers he believes in.
Dr. Cipher's weird. Alright, yeah, there's a theorem that's not particularly exciting. It basically says if you extend k by a whole bunch of elements, by n elements, to find what's the degree of that extension, it's less than or equal to the product of the degrees of their minimal polynomials. I don't feel like doing that one. Have a good day.
Wait, that's
Are we coming back to this next time, or?
We're coming to the next packet next time.
Oh, we're not doing this at all. Okay.
Well, I wanted to get through this packet today because I realized we're a little behind where I need to be, and I need to go chop a little bit. And all these side discussions about Liouville and stuff is not helping matters, and I realize that. Parker,
Yeah.
hit the video.
I will.
Hope you're doing all right, lady. I hope you have a good spring break. Do you get spring break? Hope you have a good one.
Yeah, we can make
Does she get spring breaks at the same time?
She doesn't get spring break.
In the video.
She got
He-
it.
he's-